Hello everyone, my name is Han Tan and come from TU Dortmund. Today I'm going to present our paper Surrogate Model-Based Explainability Methods for Point Cloud Neural Networks. Towards more explainable point cloud models, we propose a surrogate model-based methods and corresponding valuation metrics. We also compare how existing point cloud explainability methods perform. There are only few explainability studies for point clouds. Compared with the point cloud integrated gradients, our method has a broader applicability since no gradients are needed and is more semantic at the same time. The basic idea of LIME is to use a simple, explainable but accurate model to locally approximate the black box model. In order to make the LIME applicable for point clouds and improve its performance, the input instance is first divided into an appropriate number of clusters using k-means clustering with farthest point sampling. This would make the cluster more uniform and enhance its performance. Besides, the traditional flipping operation is simply setting the corresponding pixels to 0 or the means of the whole input. However, this does not work well for point clouds because shifting their coordinates to 0 does not actually remove them. They assemble as an overlapping point clusters which may impair the prediction of neural networks. Our solution is to simply use the adaptive input scaling property of point cloud networks to completely remove the information of the points to be flipped. The general process is that we perturb the input by randomly flipping its clusters and then use the perturbations to train a linear regressor to simulate the prediction score of the point cloud models. Then we can observe the feature importance according to the linear weights. To quantitatively evaluate the explainability methods, we propose local fidelity and probability. Local fidelity measures the prediction distance between the two models through some distance metrics and coefficients. Probability represents how the prediction scores changes during the flipping process. We suppose that flipping positive and negative attributed points will result in opposite tendencies, that flipping positive points will cause a quick drop of the prediction scores, while on the contrary, flipping negative points will make the model even predict higher scores. This is an example of explanations under different number of clusters. The red and blue points are explained to be positive and negative to the corresponding predicted class respectively, and black ones are neutral. For quantitative valuations, we set a direct transplant of line as baseline, and our modifications successfully improve the performances both in local fidelity and probability. We also compare the existing point cloud applicable explainability methods, and we find that only 3D integrated gradients and our 3D line are able to generate satisfactory explanations. Methods such as raw gradients, guided backpropagation perform quite bad and noisy. Here are the references, and thank you for the listening.